Hi everyone, thanks for attending my presentation. I'm Zheng, and today I'm going to discuss my paper named Improving Community Detection Performance in Heterogeneous Music Network by Learning H-type Usefulness Distribution. Let me first introduce the background of this project. With music becoming an essential part of daily life, there is an urgent need to develop recommendation systems to assist people targeting better songs with fewer efforts. The interactions between users and songs naturally construct a complex network, and community detection approaches can be applied to reveal user potential interests on songs by grouping relevant users and songs to the same community. And after that, we can just recommend the songs within the same community to the users. But this type of interactions are heterogeneous, which challenges conventional community detection method. So there are multiple types of the interactions between the users and the songs. And conventional community detection basically work on the homogeneous network. So it is a challenge to directly apply conventional community detections on the heterogeneous networks. So that's the intuition for us to propose a generic-based method to learn the H-type usefulness distribution. We call it ETUD on heterogeneous networks in an evolutionary manner. Using this model, we can highlight those H-types more important for music recommendations by assigning higher weights on them. And after that, all the weights are updated by multiplying related ETUD values on their original weights, and which can help to convert a heterogeneous network to a homogeneous one. And after a homogeneous network is constructed, we can use the conventional community detection method to get the user communities and for the further music recommendations. So there is an example showed in the red part of this slide. In the upper side is a figure A, is the community structure without considering H-type weights. You can see that in this graph, there are multiple types of nodes and multiple types of the edges. But if we're considering the H-type weights, so that before we have two communities, but if we consider the H-type weights, ideally we will learn higher weights on the between the user song play into a relationship, and then we multiply this weight back to the original H weights. We can retrieve the 4 different communities, and the users this time can be grouped with the 2 songs into the smaller community. And then we can better recommend these songs to the users. So this is the ideal case for our a method. And after we introduce the intuition of this project, let me introduce the details of the pipeline. So the overall model is formulated as a generic model using a evolutionary approach. So we simulate the biology evolution process happening in the real world. And it contains the several steps mentioned here, including the initialization, evaluation and selection, crossover, mutation. And we define a chromosome to represent a possible ETUD result. A chromosome is constructed by a set of the genes, where each gene refers to an H-type respectively. The value stored in each gene represents the usefulness score of a particular H-type. And if we take a look at the step in the red circle, we first initialize 4 different chromosomes. And in each chromosome, it contains 4 genes. And in each gene, it stores each gene refers to a H-type and stores the H-type usefulness score. And a chromosome is initialized by randomly assigning values between 0 to 1 to each of their genes in the beginning. And in total, in our approach, P chromosomes are randomly initialized for further evolution process. So after we initialize the chromosomes, the next part comes to the evaluation and selection. Let's first take a look at the evaluation side. So we assume that the best ETUD should be able to best reproduce users' listening history, listening preference. So in other words, we should find an ETUD that maximizes the similarities between songs ranking list generated under the ETUD and the user's actual preferences on songs. And then we come up with a Chromosome fitness score formula. This I function is the fitness score, and the personalized PageRank algorithm is utilized to represent the user listening history P as given U and W. U is the user, W is the H-type weight, and S is the song. And the NDCG at 10 is chosen as a similarity function. So, and G as given U is the actual user listening preference. So we calculate the similarity scores among all the users for their predicted learned songs ranking list and the user actual song preference, and normalize it via a softmax function on all the chromosomes. And in the end, each chromosome will be assigned with a fitness score. After we have the fitness score for each chromosome, we will select the chromosomes to generate a new generation of the chromosomes. And in generic approach, chromosomes with higher fitness score should have a higher chance to be preserved for the next round evolution. Then we use a bootstrap sampling strategy and random sample with replicates to random sample those equal number of the chromosomes based on their fitness scores. And the chromosomes with higher scores will be highly likely preserved in the next generation. And after we get a new generation of the chromosomes, we do the crossover and mutation step to generate the new chromosomes, because the initialized and selected chromosomes cannot fully cover the whole possible ETUD results. And there's a need to search the whole ETUD result space and find out the best one. So in the crossover step, all the selected chromosomes are grouped into pairs first, and the crossover transformation will be applied within pairs. So given two chromosomes in the same pair, they can exchange the values stored in parts of their genes, and then to create two new offspring chromosomes. And that's what has happened in the red circle. So partial gene values are exchanged. And the crossover happened between the chromosome pairs, and the mutation step happened within the single chromosome. It allows a chromosome to generate a new offspring chromosome within itself. For a chromosome, instead of exchanging values of genes with another chromosome, it exchanges its genes values with a random variable x randomly drawn from a uniform distribution between 0 and 1. And so the whole process is an iterative process. It will keep running for generations until the best chromosome no longer changes for n generations. And then the chromosome with the largest fitness value in the last generation will be used and returned as the final results. After I explain the model details, we test our model on a music recommendation task and using a Xiaomi dataset, which is one of the largest online music streaming service in China. And the following two tables in this slide shows the details of the dataset we are using. So you can see that we have multiple different types of node and multiple different types of ages. And the listening history of 70% of the users in our ground truth are randomly sampled to be used in our model training. because in the training process, we need to calculate the fitness score. And then the rest 30% of the users' listening history are used for model testing. And we also define two different tasks to evaluate our model performance. The task one is the searching cost with between community jumping. So it examines whether applying ETUD on heterogeneous networks can reduce the searching cost of retrieve all user listened songs. So in the music graph, each user will belong to a community after the community detection method is leveraged. When the user looks for songs to listen, there's a searching cost for the user to retrieve all his favorite songs. So we simulate this searching behavior to see how ETUD can help to reduce the searching cost when adding to existing community detection method. So all the communities are ranked by their contained number of the listened songs in a descending order. So that's the natural when user want to search for all the communities. So they first need to rank all these communities. And the searching cost function depicts how much effort users need to take to retrieve all their listened songs by jumping between the communities. They will start from the most favored community to the least favored community until all the listened songs are retrieved. And ideally, the best community structure is that all the listened songs are grouped into one single community. And this formula shows how the cost is calculated is related to the community ranking and the community size. So here is the results using before and after using ETUD on 6 different types of the base community detection algorithms. The first 3 are embedding based. So we use the first 3 methods to calculate the node embedding first and apply the k-means to generate the communities. And the rest 3 methods are just the community detection method to generate the communities directly. And we can see from the results, the cost after adding the ETUD for all the algorithms, their searching costs are reduced, which means that the ETUD actually is useful for us to retrieve the better communities within the heterogeneous network. The task 2 is the searching accuracy within community. So the task 1 is the between community, and we're also willing to see whether it also benefit music recommendation accuracy within communities. For each testing user, we select all the songs in the same community as the user and rank all the songs based on their PageRank score calculated during the training process. And this time we use NDCG at 5 to report the recommendation accuracy. Still, on these 6 existing models, we can see adding ETUD will increase the NDCG score, which means it will benefit the music recommendation accuracy. And that's all for my presentation, and thanks for listening.